Good evening, everyone. I was requested to have a look at or go through in a video one of the problems from the, or maybe I'll do a few more as well at some other point in time. But right now, I'll just go through this video, this problem in this video. So yeah, I was asked to go through some of the Martin Gardner puzzles that I posted in my previous video. At least it's my previous video at the time of recording. And this one is one that I asked some year 7s and 8s at my school because I basically just run a club. It's called Maths Challenge Club for some younger children, and I really like this question. The reason why I like this question is because it's difficult for everyone, and the solution is well, there's quite a few clever solutions actually to this problem, but the actual solution is really nice. So yeah, I mean, without any further ado, let's get straight into this. And the problem is called, and also, if you haven't already seen, I also extended this problem and tried to turn it into a map problem. Even though, of course, I do not, I'm probably not the best MAT problem writer. I myself saw a few flaws and with sort of the problem, maybe the difficulty level is not quite right, or, I haven't quite, those questions are written to be perfectly fitted into the MAT. But obviously, since I don't actually write for the MAT, I don't know, what constitutes perfectly fitting for the MAT. But I tried to make an MAT question based off of this, by extending the question and just based off of what I had seen when I was preparing for the MAT. So if you want to try that out, feel free to. I posted it on my TikTok. But without any further ado, here we go. So the problem is called the counterfeit coins, and in this sense, counterfeit, if you're not familiar with that, just basically means fake. So basically, like, this problem revolves around some coins that are fake, and your job is to basically identify which coins are fake. Okay, so also I've taken this exactly straight from one of Martin Gardner's columns. So it does say in recent years, blah blah blah. That I just didn't edit that out. Okay, but it shouldn't really say in recent years because that was written a good portion of time ago. So yeah, so it says in recent years, a number of clever coin weighing or bull weighing problems have aroused widespread interest. Ignore that. Here is a new and charmingly simple variation. Okay, you have 10 stacks of coins, each consisting of $10.50. Now I don't really, again, I've taken this straight from Martin Gardner's columns. Martin Gardner was an American recreational mathematician, so this $half concept, let's just get rid of it. Let's just say for the sake of ease here that we're actually dealing with 10p coins. Okay, doesn't actually matter. We could be dealing with 5p coins, 2p coins. It doesn't actually matter. Like, the denomination of the coin is irrelevant here. Okay, the only important thing is that we have 10 stacks of 10 coins each. We have 10 stacks of coins, each consisting of 10p coins, right? So as you can see, sort of down here, right? This picture, which is in Martin Gardner's column, or in a book actually, which I think was summarizing his columns, and it illustrates it very nicely, right? So you have 10 stacks. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's 10 stacks, and within each individual stack there are 10 coins. Okay, you can count that for yourself. I'm assuming that he's also illustrated this in such a way that there are actually 10 coins there. So maybe like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So within each stack there are 10 coins, and we'll say that each of these coins is a 10p coin. Okay, just because why not? Like, it doesn't really matter. Now one of these stacks one entire stack is counterfeit. So but you don't know which one. So basically what you're told is that you have 10 stacks of 10p coins, but one of those stacks has 10 coins which look like 10p coins, but actually aren't 10p coins, or at least they're faked 10p coins. Yeah, and they weigh, and the most important fact is that they weigh differently to normal 10p coins. But they weigh such a small, the difference in weight between a fake 10p coin and a real 10p coin is so small that it basically is like, it's very difficult for you to tell that you have a fake coin just by picking it up, right? Even though the weight is different, you wouldn't be able to tell by picking it up. So you have to weigh it, right? And that's what this problem is revolving around. And so you do know the weight of a genuine. This is $half here. What it means is a 10p coin. So you do know the weight of a genuine 10p coin. Okay, 10p coin. Right, and you're also told that each fake coin weighs 1 gram more than it should. Okay, it doesn't have to be 1 gram, but for this problem, I guess that's good because also 1 gram, you wouldn't be able to tell me, yeah, this object is 1 gram more than this one, so that forces you to weigh it. Okay, or probably wouldn't be able to tell me. Maybe one of you can tell me that, but that isn't the point. The point is that in this problem you can't. Okay, now you're allowed to weigh the coins. It says here on a pointer scale. This will also work with this sort of scale here, which is what I was thinking about, to be honest, when I did the problem. But yeah, they're both the same. There are some scales for which this doesn't work. Specifically, there are scales with basically like baskets, and if you like 2 baskets, and if you put something, if one side is heavier, it will tilt. I'm not sure exactly the name of those scales, but I'm sure hopefully you're familiar with what I'm talking about. It's just like a scale, and it's got 2 baskets, right? Instead of just like one thing where you put everything on, it's just got 2 baskets, and you can basically compare 2 sort of objects by placing one object in the left basket and another in the right basket, and then it tilts accordingly to whichever one is heavier. So that is another sort of scale. but it doesn't actually, I think, work. Or at least the solution to this problem doesn't work with that sort of scale. So actually, the solution to this problem is different depending on the scale that you use. But these two scales are different and they work. So yeah, I guess I've probably given something away as well. Maybe I shouldn't have said that, but whatever. The question then is, what is the smallest number of weighings necessary to determine which stack is the fake one? Okay, so as I said, just to repeat, you have 10 stacks. Each of the stacks has 10 coins within it, and each of the coins is a 10p coin. Not really important, but whatever. You know the mass of a real 10p coin, and you're told that one of the stacks has 10 fake 10p coins. And so what that means is that their mass is the mass of each of those fake 10p coins is 1 gram more than the mass of the real 10p coin, right? And so the mass of that entire stack is 10 grams more than the mass of the stack of just normal 10p coins, right? Again, we'll assume that's also, you couldn't really tell by picking up an entire stack that it's fake, okay? We'll also assume that. Yeah, okay, and so you're given this information, and you need to figure out which stack is fake by weighing the coins, and you're allowed to weigh coins individually as well, you don't need to weigh the entire stack. But the question is, there are multiple ways to do it. The question is, what is the smallest number of weighings necessary to determine the fake stack? Okay, right. Okay, so there are a couple of approaches to this problem. The most simple one is obviously to just take each stack of 10p coins. Okay, so you just take each individual stack of 10p coins and you place them on the scales. Okay, now because you know the mass of an individual 10p coin, the mass of the entire stack is also known to you, right? So if the mass of an individual coin, if that's x, right? If this mass is x, then you know that the mass of individual stack, which is containing 10 of those coins, stack, is simply 10x grams, right? So you'll know the mass of the individual stack because we know that you know the mass of each individual 10p coin, okay? And so when you weigh the stack, you'll know, based off of assuming that the mass is perfect, the scale is perfect, and that there's no systematic error or any random error. There's no source of error in terms of what value the scale's actually giving you. Okay, assuming that's all fine. Okay, then you'll be able to tell just from that, putting that one stack on the scale, right? That that stack is real. Okay, because you know what the mass of that individual stack should be, right? In theory, if the coins are real. So when I put a stack on the scales, I can immediately tell whether it's real or fake. Okay, because yeah, right, I can definitely tell whether it's real because I know what I'm expecting there, 10x. And if it's fake, then I would obviously, each of these coins would, instead of x, would be x plus 1, so the entire mass of the stack would be 10x plus 10. So I would observe on the scale 10x plus 10 instead of 10x, and I would be able to know as well if the stack is fake. So obviously, in the best case scenario, the first stack I pick and put onto the scales is going to be fake, in which case I'm done in one weighing. But this question, when it says what's the smallest number of weighings necessary to determine which stack is counterfeit, means across all possible scenarios, how many weighings do you need, okay, to tell me with certainty which stack is fake in all possible scenarios? Okay. Now, obviously, in this case, you might get lucky and pick the right stack the first time and place it on the scale, and then you see 10x plus 10, and you're like, oh, okay, there's the fake stack done. Fine, you're right. You may get lucky, but you may also get very unlucky. Do the same process 9 times, right? You take each of these stacks, each of the 9 stacks, right? So maybe you take, you might take this stack here, and it's fake, and it's real. Sorry. Then you take this stack here, real. This stack here is real. This stack here is real. This stack here is real, and so on until you finally get to this stack. Okay, in which case you know that it's fake. Okay, so actually that will take you 9 weighings, right? With certainty, you'll know after weighing things 9 times, right? After 9 weighings, you'll be able to tell with certainty which stack is fake. Because what I can do is I can just take each individual stack and place it on the scale, right? And because I know what the mass of each real individual stack is going to be, I can immediately tell whether or not that stack is composed of real coins or of fake coins. Okay, and so and in the worst case scenario, that will take me 9 weighings. That method, that sort of strategy, will take me 9 weighings to give you the fake stack with certainty, right? Because in the worst case scenario, like I said, each of these stacks that you pick is real until the very last 2, and then you pick another real one, and you're left with the fake one. Okay. Obviously, in the best case scenario, you pick the fake one immediately, but each strategy that I explain is judged by its worst case scenario in this question, okay? Because you need to be able to tell me with certainty after this number, right? If you were to say the smallest number of weighings is 3, then you should be able to tell me in all possible scenarios after 3 weighings which stack is fake, not just in the best case scenario, okay? So in this case, this gives you an answer of 9. Okay, now obviously, if that was the answer, that wouldn't be too interesting, and it isn't the answer, but it's a nice initial strategy, okay? And we have to think, is there a way that we can do better? And of course, yes, there is a way we can do better, because no one ever said that we need to weigh the stacks individually and that we can't actually put more than one stack on the scale at a time. Okay, and so there are methods that do better, which basically group stacks into, well, basically split the stacks into groups. So one method, which some of the people in year 7 and 8 would come up with, is as follows, right? So what they said to me is, okay, I can do this in 5. Okay, so I can tell you after 5 weighings with 100% certainty which stack is fake. Okay, and obviously 5 is better than none. So I was interested to see what they had to say. And what they told me is, okay, so the first thing I want to do is split these 10 stacks into 2 sets of 5 stacks of 10 coins. Okay, and then what I'm going to do is I'm going to choose one of these stacks, one of these sets of 5 stacks to place on the scale. Now, obviously, we know the mass of each real stack of 10p coins, right? That's just 10x, as we've already ascertained. Okay, now maybe this is the fake stack, but you see what I'm trying to say. That effectively, the real stack weighs 10x, the mass of an individual stack of 10 real 10p coins will weigh 10x grams, right? So you know what that mass is. And so therefore, if I were to put 5 stacks on the scale at the same time, you would expect that, given that all the stacks are real, to weigh 50x grams, okay? And so what you do is you put those 5 stacks of 10p coins onto the scale, and you look at it, and if it weighs 50x grams, then all of those 5 stacks are indeed real. So what you've done there is you've basically grouped the same sort of procedure that you use in the first strategy into, well, you basically use the same sort of procedure that you used in the first strategy, but used it more efficiently, because what you've done is you've grouped the stacks together, right? Which means that what you can do now, given that you know that the mass, if you did see a mass of 50x grams, is you'd be able to tell me that all of those 5 stacks, every single one of them, is real. So instead of just getting rid of 1 stack every single time, you actually got rid of 5 stacks in one weighing, right? So that's a lot more efficient, okay? And so obviously that gets rid of 5 stacks, supposing that these are real. Alternatively, if you weigh 5 stacks and you don't get 50x grams, you know that one of those 5 stacks has to be fake, and so therefore the other 5 stacks have to be real. And so therefore you'll always be able to cross off one of the 2 sets of 5 stacks using this method, okay? And then you have 5 stacks remaining, okay? So the question is how would you split these, right? And the most natural way to do this, which I think students would tell me, is to split it into a group of 3 and a group of 2. Okay, right. So now I have a stack, and now I have a group of 3 stacks of 10p coins and a group of 2 stacks of 10p coins. Okay, and I just choose one of them to place, whichever one. Let's say I choose the 3 stacks of 10p coins to place on the scale. Okay. And let's say that on the scale, obviously what I'm expecting to see, if they're all real, is 30x grams. So if I do see 30x grams, then I know that each of these is real. Okay, so in which case I can cross those 3 off. And I'm left with only 2 options remaining for which stack is real and which stack is fake. And obviously at that point, I can just choose one of those individual stacks and weigh it and see if it weighs 10x grams. If it does, then it's real and the other one is fake. If it doesn't, then it's fake and we're done. If it doesn't and it's fake, then that took us 3 weighings in the best case scenario. If it does and it's real, then it took us 4 weighings. Actually, no, sorry. In both cases, that doesn't take us 3, actually. Because, yeah, sorry, we used one initial weighing for the 5, then another weighing with the 3, and then we used another weighing in both cases to ascertain whether it was real or fake. So, yeah, that takes us 3 weighings in both cases, right? However, let's say now that instead, these 3 stacks of 10p coins, don't give us 30x grams when placed on the scale. So instead, we have to cross out these 2, okay? And then at this point, we have to further subdivide this stack of 3 into a stack of 2 and a stack of 1. And obviously, I might get lucky here. And if I put this stack of 1 onto the scale and it gives me 10x plus 10, I'm done because I know it's fake. But equivalently, if I put it on the scale and it gives me 10x, then I know it's not that, and then I have to use a further reading to ascertain which stack is real and which stack is fake. So in that case, that has taken me 4 readings. Although actually, that makes me think that always takes 4. I don't know actually how they got 5. Maybe they just miscounted actually. Now that I think about it, because 4 definitely seems possible here, because you need an initial weighing to split the 10 stacks of 10 coins into 2 sets of 5 stacks of 10 coins, and then you can root out 5 of those stacks immediately. Okay, and then you can split it into 3 stacks and 2 stacks, and you can choose one of them, right? Let's say that the 3 stacks are real, so you're left with one more weighing to determine which of the 2 stacks is real. So that's 3 weighings. And let's say that the 2 stacks are real, in which case you're left with 2 more weighings to ascertain which of the stacks is fake. And so that takes 4 weighings. So yeah, I think actually that's 4. Maybe they had another way that was 5, but that's a way that you can actually use 4 weighings to get the solution. And actually, that's quite a nice solution. And that method actually also works with the other scales I was talking about, right? The ones with the 2 baskets, which sort of tilts depending on which side is heavier. That also works with those scales as well. But there is a method which trumps this, which someone actually in the club did get. And I was pretty surprised, actually. Most of the students came up with very good ideas, but none of them really had anything too close to the answer. Now, I did tell them the answer. I didn't tell them how to get to it, though. So, yeah, one of the students getting to it was pretty nice. And, yeah, and the answer is just 1. So we have used 4 weighings here to determine which stack is fake with certainty. But in actual fact, you only actually need a singular weighing to determine which stack is fake. If you haven't already figured out what that is, I would advise that you have a think. If you have, then you can check now to see if this is the solution you came up with. And if not, then let me know what your solution is. I'd be interested to hear it. So in each of these methods that I've spoken about so far, we've been using the stacks, right, to determine, we've been sort of grouping stacks together or weighing stacks individually, and then comparing, the mass of the observed mass that we see of the stack with the mass that we expect to see if the stack was composed of real coins, okay? And that's perfectly fine, and that works. But, again, if you read into this, there is no condition which says that we have to weigh stacks altogether, right? So, for example, if I wanted to weigh, this stack here, if I wanted to, see whether or not this first stack is real, okay, I don't necessarily need to put the entire stack onto the scale, right? Even though that also works, right? What I could do is instead take a coin off the top of the stack and put it onto the scale, because that coin should weigh X. And if it's fake, then it will weigh X plus 1. We know that in the fake stack, all of its coins are fake. So each of them weigh X plus 1. So what I'm trying to get at here is that there's no condition that we have to weigh entire stacks at a time. We can weigh individual coins. And that idea is crucial for the solution. And the solution is as follows. So you have 10 stacks of 10 10p coins. And you'll arrange these stacks. Let's say that you arrange it in the same way that Martin Gardner has done so on this image here. Okay? And you'll label them. So you'll label them 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And what you're going to do is you're going to take 1 coin off of the top of the first stack, and then 2 coins off the top of the second stack, 3 coins off the top of the third stack, 4 coins off the top of the fourth stack, and n coins off the top of the nth stack. And you're going to group those coins together into one big stack and place this stack onto the scale. Now, obviously, that's only one weighing because you're only reading the scale once. Okay? So that's only one way, but you might think, what does that work? We're combining stacks here. Wouldn't that just confuse things? Right, because some of those coins will be real, some will be fake, so how are we supposed to know? And the key point here is that we've taken n coins from the nth stack, okay? And so, obviously, assuming that if we had a scenario where all of the 10 stacks were real, then what we would observe is the following. We would observe x plus 2x plus 3x plus all the way up to plus 10x, right? Which is just x times 1 plus 2 plus 3 plus 4 plus all the way up to plus 10, which is just x times 10 times 11 divided by 2. This is just the standard formula for the sum from 1 to n, where n is 10. It's just n times n plus 1 over 2. So the mass that we would expect is 55x grams. Okay, if all of the 10 stacks are real, okay, because we're taking x off of stack 1, right? So that's just 1 coin, which weighs x grams if it's real. And then 2x from stack 2, so we take 2 of the coins from that stack, then 3 of the coins from the third stack. So if all the stacks are real, you would observe this mass, 55x grams. Now, obviously, we know that one of the stacks is going to be fake, so we're never actually going to observe this mass, okay? It's a purely theoretical mass that we would observe if every stack was real. But what we can play around with here is we can see how much the mass that we observe deviates from this value if we take n coins from the nth stack and combine them into one big stack and place them on the scale. Now, suppose that the fake stack is the first one. Then instead of x, I'll have x plus 1, because the coins in that stack will weigh one more gram than they should, right? Because they're all fake. Okay? And so I have the x plus 1 plus 2x all the way up to plus 10x. Now this is just going to be x plus 2x all the way up to plus 10x plus 1. So just 55x plus 1 grams. Okay, so if the first stack is fake, then I observe this value. If the second stack is fake, right, then what I'll observe is x from the first stack, right? So I take 1 coin of the first stack. Then I take 2 x plus 1s from the second stack, right? Because 2 coins of mass x plus 1 I take from the second stack. So their total mass is 2 times x plus 1 grams, plus 3x all the way up to plus 10x, right? And 2 times x plus 1, that's just 2x plus 2. And so I can combine these things again, and actually what I'll get this time is 55x plus 2 grams. Okay? Now you can repeat this process assuming that, whichever stack you want is fake, okay? And in each scenario, right, if the nth stack is fake, nth stack fake, then the mass that you'll observe, right, given that x is the mass of a real 10p coin, is exactly 55x plus n, right, grams. So all you need to do is determine what this n is. In other words, figure out what 55x is, if you're given that you know the mass of an individual real 10p coin. Figure out what that is. Weigh this new stack that you've composed by taking one coin, the n coins from the nth stack, and combining them into one big stack and placing those on the scale, and then see how that value that you've observed differs from 55x. Now, if it differs by n, right? So if you calculate what that n is, then you'll be able to know that will uniquely identify which stack was fake, right? Because that n contribution is exactly coming from the fake stack, because we know that each of the fake coins weighs 1 gram more than each of the real coins. And so by doing this, by combining actually these coins into one big stack and observing the difference in that mass, and then observing the difference in mass, from a theoretical mass that would be achieved if every single stack was composed of real coins, which is 55x grams. So taking your observed mass and taking the difference between that and this theoretical mass, which would be achieved if every single stack was composed of real coins, we can figure out what n is, and then n is just the specific stack, as I've illustrated here with the cases with the first and second stack of fake. So n is just the specific stack which is fake. So it'll just be some number from 1 to 10. Okay, and so that is a way where you'd be able to use these scales to figure out which stack is fake using only a singular weighing. Now, I'd be interested to know if there's any other solutions to this problem, but this is a really, really nice solution I found. And it's one that's actually very difficult to think about, but it doesn't require any, profound mathematical insight or extra knowledge. It really only just requires, good problem-solving ability, good ability to think. And that's true of most of Martin Gardner's problems, and it's why I like his problem, because they just require, problem-solving, but at a level which doesn't really, take any, which doesn't expect anything of you, basically. So it's problem solving, but without any expectation of knowledge, rather just raw problem solving. And I think that those types of questions that's why I give them to my year 7s and 8s, because they're suitable for anyone and everyone. And that's why I really like his problems. Okay, enough waffle though. And obviously another thing to note here is that this obviously doesn't work with the scale that I spoke about, which tilts to the left or right, because you wouldn't be able to observe the specific mass, right? This idea here, 55x plus n and 55x, only works if you know, right, the specific mass of the new stack that you create by taking n coins from the nth stack, right? So in each of these cases where I have a digital mass, right, a digital scale, sorry, I can actually observe the specific mass of that new stack that I've created. Whereas with the other method, there's no way to do that. It only really works, that scale, which tilts, for comparing two different groups of coins, right? So it would work, for example, if I had 5 stacks on the left and 5 stacks on the right and one tilted one direction, then you'd be able to tell that the fake stack lies in that basket, basically. However, because it doesn't actually give us the real mass, right? It doesn't tell us, we aren't going to be able to figure out this 55x plus n, and so therefore we won't be able to figure out n, because it doesn't give us the real mass. And so as a result of that, I don't think, if I'm correct here, which I've only really thought about this in my head, but it makes sense that this method that I've just gone through that gives you the answer in one weighing is actually not doesn't work with that sort of scale. So yeah, unless you figure out 55x and you somehow find another object which weighs 55x and you place it on the scale and you see if it balances, and you do the same with 55x plus 1, 55x plus 2, but I feel like that's cheating and that would take more than one weighing anyway. So yeah, it doesn't necessarily work using those scales, but using these scales, which is why I emphasized this point at the beginning, it does indeed work. And so the answer to the problem is just one weighing. And that is a really, really good problem from Martin Gardner. I recommend you check out my MAT style problem as well that I made from this, because it just extends this idea into with other scenarios. So yeah, it's cool, pretty nice stuff.